Hello everyone, I am Biruk Asmare. I am a PhD student at Polytechnique Montreal. Today I'm going to present our work on the prevalence, impact, and evolution of SQL code smells in data-intensive systems. So code smells are poor solutions to recurring problems that could have an impact on performance and maintainability in the long run. There are different examples of code smells such as complex class, long meta, shotgun surgery. There are more than those smells which are discussed in different information sources. One of them is Refactoring, book by Martin Fowler. We are particularly interested in SQL code smells, which are a special kind of code smells that are related to database access. So those smells could be in the data definition as well as data manipulation. We are particularly interested in four SQL code smells. Those code smells are obtained from the book Bill Carwin, SQL Anti-Patterns. The first type is implicit co-elements smells, where we fail to mention the co-elements explicitly. So if we have, for example, a large number of co-elements, a table is a large number of co-elements, then if you are interested on few number of co-elements, then it will unnecessarily query all co-elements, which could cause performance problem. The other thing is if we restructure the co-elements as part of the database change, and if the front end is not aware of it, then it will also create a functional bug. The other type of smell is fear of the unknown smell. In this case, if we do not correctly perform null check, then we will get a result that is not in agreement with our query. For example, in the second case, if the customer ID can be null, then the not operator will return unknown, which forces the database to return an empty result set, even though there are customers with ID different from 5. The third type is ambiguous groups, where we have a group by statement in our select query, and if we include co-elements that are not part of group by or the grouping operator, then the database just randomly picks one value, which is really not deterministic. For example, in this case, if employees have more than one phone, then if we do the group by their name, then the database is going to pick one phone number, random phone number. The fourth one is random selection, where we need to fetch one random single row, but to achieve this operation using the run function, it requires a reordering of those tables, which is costly in terms of performance. So traditional code smells are well studied, their detection, their impact on maintenance effort, their impact, their evolution, or the lifespan of code smells, as well as their impact on software change proneness. But when we come to SQL code smells, there are few studies that particularly focus on SQL code smells. The first one is on the data definition part, where the paper smell relations, they studied the smells related to database schema, so related to database creation. The second one is prevalence of bad smells on PL SQL projects, where they studied 20 PL SQL based projects and studied the prevalence of bad smells. So we can see that those SQL code smells related to data access, especially those SQL code smells embedded as part of data access code, are not particularly addressed in the literature. To address this gap, we particularly study the impact of prevalence and the evolution of SQL code smells embedded in data access queries. This is particularly important because the data-intensive systems, which are the context in our case, are highly reliant on the efficiency of database access. In this paper, we answer 4 research questions. The first one is deals with the prevalence of SQL code smells across different application domains. In the second one, we study the co-occurrence of SQL code smells with traditional code smells at a class level. And in the third one, we study the co-occurrence of those SQL code smells with bugs. And lastly, we discuss how long those SQL code smells survive. So we study the evolution of code changes in our sample projects and see if those SQL code smells are getting fixed as part of the evolution. In our approach, we first collected projects that are related to database access or data-intensive projects based on their database access technology, such as SQLite, JDBC, JPA, and Hibernate. And we came up with more than 30,000 projects. And then we collected the import statement as expected by our SQL smell detection tool and ran a code search on those projects. And as a result, we find 800 projects that contain those required import statements. And from those 800 projects, we rank them based on the number of queries to represent if they're data intensive or not, and collected 150 relevant projects for our study. And then in the second stage, we did a code smell detection. For the traditional code smell detection, we used Decore, and we used SQL inspect for SQL code smell detection. And we took a snapshot of each project every 500 commits to get different snapshots for each project. And for that, we need to track changes such as renaming, addition, and deletion. So we have implemented that logic. And thirdly, we collected bug inducing commits from bug fixing commits in those projects, and we identified bug fixing commits using keyword based approach. And we linked those information obtained from the smell detection, file evolution, and mining bugs, and build our data set. And then we performed a different type of statistical analysis to answer our research questions. When we see the details on our sample projects, we divided them based on their application into 4. You can see that the median database access query count for each group of projects, for example, in utility and business, is higher. And we can see that on average, we have 146 kiloline of code projects with 121 SQL queries and 15 DAO classes. And in some cases, we have 48% SQL queries where 11% of them have complex subqueries. So we can see that large portion of those projects are libraries and frameworks. To answer the first research question, which is the prevalence of SQL code smells on our different application domains, we compute prevalence on latest version of all snapshots for all projects, and we compute the prevalence as the ratio of total number of SQL code smells to total number of database access queries. The table shows that the prevalence, the median as well as the mean prevalence in percentage for those 4 application groups. Business applications have the highest prevalence of 3% with a mean value of 8%, and followed by the utility, which has a median prevalence of 1.68%. In the graph, we see the distribution of implicit Khomh smells across those 4 application domains. There are some number of outliers which have a higher or significantly higher prevalence compared to the average or the median. So in those cases, the severity and the impact could be higher. To check the actual impact of this implicit Khomh smells, we randomly selected 98 of those smells and ran a manual analysis, and found that in 70% of cases, they queried more than 3 columns that are not necessary, and in some extreme cases of 15%, they queried more than 9 columns that are not necessary. Similarly, for fear of unknown case, the prevalence is close to 0, the median prevalence, but we see that there are a significant number of outliers. And in other cases, the prevalence, we didn't see any number of occurrence in the latest versions. So we can see that implicit Khomh smells are the most prevalent, and therefore developers need to focus on those. In the second research question, given those SQL code smells are prevalent in our data-intensive system applications, we see their co-occurrence with traditional code smells, and we run a priori association rule mining. We see that in the table, given the lift and leverage values, the leverage value is close to 0, which indicates a small association between SQL code smells and traditional code smells. Even though a priori association provides shows that there is a small association, we don't know if it is statistically significant or not. So we ran a chi-square p-value and found that in some cases, for example, implicit columns and log parameter list, we have a statistically significant co-occurrence. But we need to consider the sample effect. So we ran a Cramer's V test of association, which shows in most cases a weak association of less than 0.1%. So we can see that traditional code smells could co-occur in some cases with SQL code smells. However, their association is rather weak. And thirdly, we studied the occurrence of SQL code smells with bugs to see if there is some kind of potential correlation between SQL code smells and bugs. And we ran chi-square statistical test and found that SQL code smells do not have significant co-occurrence with bugs. On contrary, traditional code smells such as complex Elixir and long parameter list have the significant co-occurrence, and we can see similar results for Cramer's V value. We also ran feature contribution based on random forest model, and we found that again the traditional code smells are more associated with bugs compared to SQL code smells. To study those, we use file versions that are mentioned in bug-inducing commits, which are 3,000 out of 21,000, which are not mentioned in those commits. So you can see that SQL code smells do not have a statistically significant association with bugs. Lastly, we study survival of SQL code smells to see the evolution, to study the evolution of the project and analyze if those SQL code smells are getting fixed as the projects evolve. The graph shows the Kaplan-Meier survival curve of implicit column smells. On the x-axis we found time, and on the y-axis we have the survival probability. We can see that in the first few days there are a significant number of censored projects, which shows that the project's observation window ended without getting the smells fixed. The same goes for fear of unknown smells, but in this case we can see the steps as there is a small number of occurrences in our projects. For those SQL code smells, we observed that more than 80% of source code files contained implicit elements in all tracked snapshots, and 65% for fear of the unknown, and more than 89% had those SQL code smells introduced in their first tracked version. To see which one are getting more attention among SQL code smells and traditional code smells on developers, we compare the survival curve of both. This graph shows that traditional code smells has a steeper slope, which means they are getting fixed quickly compared to SQL code smells. To see if the graphs are statistically different, we ran a log rank test and found out that indeed the graph is statistically different, which shows that SQL code smells are getting less attention compared to traditional code smells, and also both code smells are getting small attention in refactoring. So we can see that SQL code smells survive longer compared to traditional code smells, and large portion of SQL code smells persist throughout the changes. One of the important takeaways from our paper is that SQL code smells in general and implicit column smells in particular exist persistently in data-intensive systems. As a result, developers need to be aware of them and consider them for fixing. We showed that traditional code smells and SQL code smells do not occur together, which shows that we need to give a particular attention, separate attention for traditional code smells and SQL code smells. The other point is that we explored the co-occurrence of SQL code smells with bugs, but other aspects of software quality needs to be explored in the future. Lastly, we say that developers need to be aware of SQL code smells, especially in data-intensive systems, and refactor them in order to avoid potential harm during the development as well as operation of data-intensive systems. Thank you for your attention. For further information, contact us or check out our replication package at GitHub.